If you're serious about machine learning, weight of evidence is a technique you must know. It improves feature quality, reduces noise, and helps models learn more effectively. In this video, we'll see how the weight of evidence, or WoE in short, works, and implement it in Python with examples. This is one tool that will elevate your machine learning model performance instantly. Weight of evidence is a technique used to transform independent variables into a standardized scale. It measures how much evidence a specific grouping, or bin, of data provides in favor of a target outcome, usually good versus bad in a binary comparison form. The formula is calculated as the natural logarithm of percentage of good divided by percentage of bad, where percentage of good is the number of goods in bin I divided by the total number of goods, and percentage of bad is the number of bads in bin I divided by the total number of bads. While WoE describes the predictive power of a specific bin within a variable, information value, or IV, describes the predictive power of the entire variable. It is basically a weighted sum of the WoE values. The formula for IV calculation is as follows. An advantage of information value is that it comes with a standardized rule of thumb for interpretation. Using the table, it helps to objectively assess if a variable is useful or not. Now, we can begin to code in Python by first importing the libraries which we will be using. The main library which we use is Scorecardpy, and we will suppress the warnings, as there may be many that might pop up through the use of the library. For those who are unfamiliar, Scorecardpy is a library developed to do credit scoring. We can use the directory function to see what modules and functions are available in this library. We will be using some of these functions in the video today. I will provide the link to the Scorecard project in the description box. For a start, the library provides a toy dataset. We can load it using the German credit function. It is a credit score dataset, with the target column being creditability, and it has 21 columns. To preprocess the data and ensure that it is in a format that can be ingested for weight of evidence binning, we will need to pass the dataset through the var filter function and specify the target variable as an argument. Notice that after passing through the var filter function, the number of columns have reduced from 21 to 14. This is because columns that do not meet the preprocessing requirements are removed. If we use the help function on the var filter function, we see that there are some criteria that are used to filter and remove columns. For example, we can see that there are thresholds for parameters such as for limit, missing limit, and identical limit. To determine the reason for exclusion, we can rerun the var filter and set the argument return rm reason to true. The output is a dictionary with keys dt and room. What we are interested in is the values of room. When we output the rm values, we can see a data frame, and the first 7 rows are the stats of the removed variables. Under the rm reason, we can see the reason for exclusion if applicable, along with the corresponding computed values for filter criteria. Now that we have a basic understanding of the var filter function, we can start to use the Scorecardpy module for feature engineering and selection. We will not be using the German credit dataset for this, and instead we will look to another toy dataset, the breast cancer dataset, to show that this module can be used for other use cases apart from credit scoring. This dataset has 31 columns, including the target column, which is the dependent variable. Then, we will run the same var filter function to preprocess the data so that it can be binned properly. We will also replace spaces within the column names with an underscore. This is necessary for the VIF function, which we will use later on. We can see that the result also has 31 columns, so all columns are in the right format. We will also split the data into a training and test set, as we will be running a logistic regression model later. Once that's done, we can apply the WoE bin function, passing the data frame and dependent variable target as arguments. You can see that the result of it is a dictionary, with the variables as keys with a lot of information as values. We can inspect one of the keys' worst perimeter to see what are the output results of the WoE binning. There is a lot of information here. We can see the bin ranges, with the distribution and counts, and also the WoE value, bin IV and total IV. These are useful information in determining which features are good at predicting the dependent variable. One important thing to note is the formula used to compute the WoE value here. If you remember the compute formula at the start of the video, it is calculated as the natural logarithm of the percentage of non-events, or good events, divided by the percentage of events or bad events. However, if we refer to the help information on the WoE bin function, we will see that the default computation formula is actually the inverse, and we have to set the argument to flip it around. Despite the difference, it can still be used as it is. We can perform the calculation for WoE bin and IV value to see if they check out. First, let's calculate the count of good and bad events. Then, we will use the first bin of the worst perimeter variable as an example. We will plug in the corresponding numbers using the WoE formula, and we will get 3.806485, which matches with what we saw in the previous table under the WoE column as well. Next, we can do the same for bin IV calculation by plugging the corresponding numbers to the formula, and we get 2.262904, which matches with the bin IV value as well. To get the information value for this variable, we can sum up the bin IVs across all the bins. We can verify this by performing an equality check, and it checks out. Then, we can summarize the information values of each feature and sort them by descending order. We can look at the top 10 features that have the highest predictive power for the target variable. The feature with the strongest predictive power is the worst perimeter, and we can see that the top 4 features have close information values as well. We can also plot the WoE bin plot for visualization as well. We will plot the top 10 features, but you can try to do that for all the features to see the results. The bin plot is a bar plot with quite a bit of information provided. Using the worst perimeter as an example, we can see the information value is provided at the top of the chart. Next, we see the bars are grouped by the binned range on the x-axis, with red color being the bad target and blue color being the good target. Along the y-axis, we see 2 scales, bin count distribution on the left and bad probability on the right. The number on top of each bar shows the bin count distribution. Using the first bar on the left, it means that 38.7% of the sample population has a worst perimeter within -infinity to 90. This is calculated by 154 divided by the number of records, which is 398. The blue line denotes the proportion of bad dependent variable within the bin. Using the first bar on the left as example again, the probability, or proportion of 98.7%, is a result of 152 bad targets divided by a total of 154 targets within the bin. Now, we can train logistic regression models and compare the performance of it using different input features. First, we will train a logistic regression model on all the features available, as it is at the moment, which is the data post-preprocessing of the var filter function. We will also create a function to show the model performance for evaluation, using accuracy, precision and recall to compare training and test dataset performance. Once the function is ready, we can apply it to the model we trained previously and assess the performance. The model performance is not too bad, though we can see a slight dip across all metrics in the testing dataset. We can train a second model, this time using the features with WoE values calculated earlier on. We will use the WoE bin ply function to preprocess the data. This transforms all the raw data of the features into WoE values according to their respective bin ranges for each feature. Once done, we will train the model with the transformed WoE values as inputs and output the results as well. Similarly, there is a slight dip across all metrics in the testing dataset. But, we can see an improvement in the metrics compared to the model trained on raw data. This shows that there is value in using WoE values as feature inputs, and it can help to improve model performance. Lastly, we can also use the variance inflation factor function to assess correlation, to prune the number of features used in the event that a lightweight model and data is preferred. We can run through all the variables and compare it against the target variable to see which has the highest correlation, which will indicate which has the best explainability for the target variable. We can sort by variance inflation factor in descending order to get the top few features with highest correlation with the target variable. The VIF values are significantly higher than normal, but for this dataset, we will make do with it. Based on the top few features with high VIF values, we will select only the top 5 for feature inputs. We will proceed to split the dataset into training and test set, and split it into WoE bins to take a closer look at the data. We can apply the same codes we used previously to inspect the information values and bin plots as well. Lastly, we will train another logistic regression model using these 5 features as input only and output the results. We can see that just using these features, the model still has a respectable performance metric, with all metrics above 90%. Comparing the 3 model performance results, we can see that the model trained using WoE values have the best results, showing that using WoE values as features is a viable option. Next, we can also see that using the top 5 features via variable inflation factor is able to give using all the features to train the model a run for its money, as its performance is comparable to the latter while using lesser features and compute power. And that's the end. Hopefully this has been helpful to you. For those who are interested, I will be sharing the link to my notebook in the description section of the video. Do you have any thoughts on it? Feel free to comment in the comment box down below. If you liked this video and would like to see more content of this nature, please be sure to like and subscribe as well. Thanks for watching, and until next time.